This is 1 kilogram of uranium, and this is 1 kilogram of sugar. According to Albert Einstein's famous E=mc squared, if you convert their entire mass into energy, they would both produce the same amount of energy. Now, converting their mass into energy is easier said than done, especially for sugar. The atoms that sugar is made up of are stable and require enormous amounts of energy to begin with in order to break it up, which kind of defeats the purpose of converting it into energy. But why would we want to break up or split the atoms? Scientists discovered that by splitting an atom, it causes it to break up into 2 smaller atoms. However, if you were to add up the masses of these 2 smaller atoms, they would weigh less than the original atom. But where did this missing mass go? The missing mass was converted into energy. And this is where Einstein's E=mc squared equation can be used to figure out how much energy was produced. But just how much energy can be released though? Well, to put it into perspective, you would need to burn 10,000 kilograms of coal to fully charge 1 Tesla Model 3. But 1 kilogram of uranium could fully charge 300,000 Teslas. So why is it that the metal uranium produces so much energy? An atom of any element consists of a nucleus and electrons. While electrons exist in regions that surround the nucleus itself is at the center and is made up of smaller particles such as neutrons and protons. Neutrons have no electric charge, while protons contain a positive electric charge. And the neutrons and protons that make up the nucleus are strongly bound together. But we have to wonder why an atom's nucleus doesn't just instantly break up. I mean, an atom's nucleus is made up of protons and neutrons. And although neutrons have no charge, protons are positively charged. Shouldn't charges that are the same repel each other, like the same end of 2 different magnets? The reason they don't is because of something known as the strong force. Unlike electromagnetism or gravity, which you can see on a daily basis, the strong force, although powerful, has a very short range. In fact, the range of the strong force is approximately 10 to the power of -15 meters. This is also known as a femtometer. The strong force is one of the 4 fundamental forces of nature. It is responsible for binding neutrons and protons to create atomic nuclei. You can think of it as a force that beats other forces and takes over when particles are really close together. The tiny range of the strong force is very important in this discussion. This range is the region at which any particles lying within it will be governed by the strong force. Any particles outside of this range will be governed by electromagnetism and gravity. So why is this range important when discussing why an atom splits? Let's take a look at a uranium atom. A uranium nucleus is huge when compared to other nuclei. In fact, it contains 92 protons and 146 neutrons. And if we were to compare this to an oxygen nucleus, which is made up of 8 protons and 8 neutrons, the sheer size of a uranium nucleus becomes even more apparent. If we were to measure the width of a uranium nucleus, it would be approximately 11 femtometers. Remember what we said about the range of the strong force? It's 1 femtometer. So this means there are parts of a uranium nucleus that fall outside the range of the strong force. This is why uranium is radioactive and constantly emitting particles. The protons that reside outside the range of the strong force are constantly being shot out due to the electromagnetic force. But how can we use this instability to our advantage? Scientists discovered that if you were to launch a neutron at the right speed into a uranium nucleus, you could destabilize it by warping its spherical shape, causing large parts of the nucleus to fall outside the range of the strong force, which in turn allows electromagnetism to push them apart, thus splitting the atom into two smaller atoms and releasing vast amounts of energy. If we look at the fission of uranium-235, it is split into krypton-92 and barium-141. Calculating the mass before and after the fission, we can see that 0.2 atomic mass units, or 3.32 times 10 to the power of minus 28 kilograms of mass, is lost and converted into energy. This might not seem like much, but using Einstein's E=mc² formula, we can calculate that one atom releases approximately 2.6 times 10 to the minus 11 joules. Again, this doesn't sound like much, but when you realize 1 kilogram of uranium contains approximately 2.6 septillion atoms, the energy released per kilogram is mind-staggering. This entire process of splitting an atom is known as nuclear fission. So how do we go from this to this? When a uranium nucleus is split, something else is released other than energy and two smaller atoms. 3 neutrons are also shot out. These 3 neutrons go on to destabilize 3 other uranium atoms and causes them to split, which then release a total of 9 neutrons that go on to destabilize more uranium atoms. This whole process happens in a trillionth of a second and is known as a chain reaction. When nuclear fission is uncontrolled, it leads to devastating results. As we've seen in Oppenheimer, achieving this is not an easy feat and requires an entire industry to even begin doing. Nuclear weapons are an unfortunate product of discovering how to split an atom. But this is when uncontrolled fission takes place. So what happens when we control the fission? Well, in this case, we are able to harness and produce vast amounts of energy that can help power society and our lives. So how do nuclear power plants harness the energy produced by fission? During the fission process, when a chain reaction begins, the neutrons that are shot out, causing other atoms to split, need to be controlled in some way. If we can reduce the amount of neutrons splitting other atoms up, we can slow down or even stop the fission process from escalating. In nuclear power plants, we use control rods made of boron that are used to absorb these neutrons. This stops the chain reaction and prevents further atoms from splitting. Raising the control rods speeds up the chain reaction, and lowering them slows or even stops it. This control process is extremely delicate, and if not managed properly, results in a meltdown like the disastrous events of Chernobyl. So how do we actually extract energy from a nuclear reaction? Well, during fission, a lot of heat energy is released. This heat energy is directed to a water supply, which evaporates into a high-pressure steam that goes on to power a turbine. Think of a wind turbine that revolves using the wind, but in this case, it is steam from the heat of the nuclear reaction that causes the turbine to spin. This is how electricity is generated. Although nuclear fission produces vast amounts of energy, it also produces nuclear waste, which, contrary to popular belief, is rather straightforward to get rid of and not more hazardous than other toxic industrial waste. Although it's not ideal as the nuclear waste remains active for billions of years, safe methods for the final disposal of high-level radioactive waste are technically proven, and the international consensus is that disposing it in a specifically selected geological location is the best path to take. Some people often ask, why can't we just send it into space? Well, for the very simple reason that if a rocket carrying radioactive material into space exploded, we'd have a disaster of epic proportions to deal with. An alternative form of nuclear energy that produces no waste, and a lot more energy, is the process of nuclear fusion. If you've liked this video and would like to see me create another video on nuclear fusion, let me know in the comments below. Liking this video and subscribing is a very simple way to support this channel. I'm very grateful to all of my current subscribers and to you for watching this video. Until the next video, take care.